All right, so in example 3, we have a trough that is 10 feet long and 6 feet across at the top. Its ends are isosceles triangles with an altitude of 4 feet. If water is being pumped into the trough at a rate of 9 cubic feet per second, how fast is the water level rising when the water is 2 feet deep? So I'm going to start just like before by drawing a picture so I can kind of see what's happening. We have a trough, and its ends are in the shape of isosceles right triangles, something like this. It says that the trough is 10 feet long. Draw that in there. Something like this. The trough is 10 feet long, so 10 feet, and 6 feet across the top, 6 feet. And its ends are isosceles right triangles with an altitude of 4 feet. And we have water that's being pumped into this trough. So we got water flowing into it. So we have some water in here. And that water is being pumped in at a rate of 9 cubic feet per second. So that's the rate that they have given us. I'm going to go ahead and write that down. We are given the rate of change of the volume of the water in the trough. We know that the water in the trough is going to be increasing at a rate of 9 cubic feet per second. So I'm going to call it dV for volume, dt. The rate of change of the volume of the water with respect to time is 9 cubic feet per second. Positive because the volume of the water would be increasing if water is being pumped up. They want to know how fast is the water level rising when the water is 2 feet deep. So I'm just going to we'll let this distance from here to here be the height of the water level. We'll call it h. So what I'm trying to find is the rate of change of that water level, the height of the water with respect to time. And I want that information when the height of the water, when the water depth, when h is 2 feet deep. So I need something that relates the volume of the water in the trough to the height of the water. And I know that the volume of the water is going to follow the volume for a prism. The volume for any prism is going to be big B times h, where big B represents the area of the base, in this case, the area of that triangle, times its height. Well, the area of the triangle is going to be 1/2 base times height. So I'm going to put in another variable. I'm going to let this distance, that base of the water, how wide the water is across at the top where it's filling the trough, we're going to call that B. So the volume is equal to the base, or sorry, 1/2, this is a triangle. So the volume of the base, the area of the base is 1/2 the base of the water, B, times the height of the water, H, times the height of our prism. And in this case, the height of the prism, regardless of what our water level is or how much we have, is always going to be that constant 10 feet. And so remember we said before that if the value is constant, if it doesn't change in the problem, we can use it from the very beginning. So this H represents the height of the prism. Regardless of the water level, the height of this prism will always be 10. So if I clean this up a little bit, I have 1/2 times 10 is 5 times B times H for the volume of the water that's in the trough. Now I have a problem in that I have a relationship between V, whose rate of change I know, and H, whose rate of change I want to know, but I also have this extra variable B in here. So I need to come up with a way of eliminating that variable. So if I go back to my picture, I notice that even though the whole thing is 6 and 4, that's not going to represent the base and the height of my water. However, I do have similar triangles, which means I can set up a proportion. So if I look at the base of the whole trough, the altitude is 4 feet, The width is 6 feet, not drawn to scale. And that's going to be proportionate to the base of my water, whose height is changing, and we called it h, and whose base would also be changing, and we called that b. So if I set up a proportion, the proportion of the base b to the height h is going to be equal to the base of our hole trough, 6 feet, over the height of our hole trough, 4 feet, or 3/2, which means that B would be equal to 3/2 times H. So I can take that information and plug it back into my equation to eliminate the variable B. So the volume is 5 times B, which is 3 halves, again, 3 halves H times H. So we get that the volume is 15/2 times the height squared. Now that we have an equation that relates V, whose rate of change we know, and H, whose rate of change we want to know, we're ready to differentiate everything with respect to time. So the rate of change of the volume with respect to time will be equal to 15 times H times the rate of change of the height with respect to time. I know that the rate of change of the volume with respect to time is 9 cubic feet per second. And I'm looking for dH dt when the height is 2 feet. So I have that 9 equals 30 times dH dt. So then dH dt would be 9 divided by 30, or 3 divided by 10. Our height would be measured in feet, and our time is measured in seconds. So the water level, the height of the water, is rising at a rate of 0.3 of a foot per second.